Welcome to the intersection of technology, cybersecurity, and society. Welcome to ITSP Magazine. You're listening to a new episode of Stories from Space podcast, where your host, Matthew Williams, examines the history of human spaceflight, the breakthroughs that revolutionized our understanding of the universe and our place in it, and the brave individuals who work tirelessly to advance the frontiers of our understanding. Knowledge is power, now more than ever.
Hello all, and welcome back to another episode of Stories from Space. I am your humble narrator, Matt Williams. Joining me today is science communicator, author, and astrophysicist, Ethan Siegel. Ethan, welcome aboard.
Yeah, thank you for having me here, Matt. It's my pleasure to be on your podcast and a pleasure to get to share a little bit more about this universe with everyone who's tuning in.
To give our guests, you're definitely a household name when it comes to science communication, but to be specific, you are the science writer for Forbes Magazine. You are the publisher of the column Starts with a Bang, in which you talk about cosmology and the Big Bang Theory and all things related. And you've authored several books at this point. What else would you say about yourself if you were forced to give a brief bio?
You know, I've always been in love with understanding the universe, what it is, where it comes from, how it got to be the way it is, and what its ultimate fate is. And I studied physics as an undergrad. I was interested in cosmology, but it wasn't until I had graduated and I was teaching public school that I realized, like, oh no, there's more I want to learn. There's more out there that I'll feel like my life is incomplete if I don't go out there and learn it. And I learned, like, what I am really interested in. These big questions are not questions for philosophers or poets or theologians anymore. They might have been for millennia, but now there's a branch of theoretical astrophysics called cosmology, and you can specialize in that, and you can study that and study its various aspects. And so I did that, and I got my PhD. And while I was working as a research associate, I realized that I had more of a passion for science communication and reaching a larger audience than I did for educating college students. And so I have slowly transitioned into that world full time. I've been running Starts with a Bang and writing it for over 14 years now. And like you said, the rest is history. And I've just been sharing what we know and how we know it about the universe with anyone and everyone willing to listen.
Yeah, this research assistant job, was this through Fermilab?
No, I had worked at Fermilab previously. I was a postdoctoral research associate at the University of Arizona during that time, and I wound up actually becoming a physics and astronomy professor up in Portland, Oregon from 2008 until 2015. And it was 2015 that I taught my last class and transitioned into doing science communication full time.
With the exception of your extensive astrophysics background, it sounds like we had a very similar pathway there, because I was also a teacher before becoming a science communicator full-time. However, yes, your science background, it is rather deep. And in terms of the theories you studied, a major one was cosmological perturbation theory?
Yeah, so that basically means, okay, we know on average, you look out at the universe and you say on the big, large scale average, it's the same. It's the same in all directions. It's the same in all locations. There are little imperfections in there, things like humans and planets and stars and galaxies. And also on the other side, like great cosmic voids or regions where there are nothing. And when we say cosmological perturbations, we mean departures from uniformity, things that are imperfect, and gravitational imperfections just grow and evolve over time. And so that was one of the things that I specialized in when I was getting my PhD, and it includes things like dark matter and inflation and the origin of these imperfections. And this is sort of the big existential questions that I love thinking about is where did these imperfections come from? How did they grow up to create the universe we have today? And what is the physics that governs them? You know, we're not just sitting around throwing out ideas. We have a whole universe to go out and observe and compare this to. And that's one of the most exciting things that are out there for me as far as science goes, is knowing that all of these ideas that we can come up with, they are always going to be constrained by the reality of the universe we actually have.
Mm-hmm. So on a scale of 1 to 10, how excited would you say you are personally about the James Webb Space Telescope and all the questions it's going to help us address?
Probably about 47 on a scale of 1 to 10. I have been pretty excited for the James Webb Space Telescope since before it was named the James Webb Space Telescope, back when it was known as the Next Generation Space Telescope. And so, you know, this is a project that I've been following very closely for probably close to 2 decades now. And I am so pleased that it was completed, it was launched, and now it is performing really better than anyone ever anticipated. And we have the first, at the time of this recording, we have the first few days of science operations behind us, and we've seen a few images from that. But we have more than 2 decades to look forward to. And so in terms of what we're going to learn, there are some enormous questions that I'm so excited we're finally going to be capable of answering.
Now, so when these images were released, did you feel that sense of relief where it was like, all these years, here we are?
You know, it's more than relief, right? Relief is what you feel when you're really worried, like, oh, it's not going to work right. And then you see it and you go, oh, phew, it worked right. That sense of relief I had was really back on Christmas Day last year when the James Webb Space Telescope launched. When I saw the launch going successfully and every stage was working as it was supposed to, and then the observatory was released from the rocket and you could see it glittering away as it floated away in the sunlight, and then the solar panels came out, that was relief for me. That was the relief I got. Seeing the images now, these first science images, it's not relief. It's like that feeling when you're really hungry, where you haven't eaten all day and it's the end of the day and you finally make it to sit down and someone puts a plate of food in front of you, and it's not enough food, but it's something that's just in front of you. That's what getting that first data from James Webb feels like. Getting that data from JWST makes me feel, wow, like I've been waiting so long for this and now I get to feast on it. And thank goodness there's more coming too.
Yes, I understand. That's a perfect metaphor, really. Yes, also a glass of water after you just cross the desert. Yeah, so getting into your writing that you've done over the years there. Now, you've published several research papers, all of which had to do with the big questions of the cosmos. And the book that you released in 2015, Beyond the Galaxy, How Humanity Looked Beyond Our Milky Way and Discovered the Entire Universe. Was that your first book?
Yeah, that was my first book. And I actually got the idea for it because someone was sort of wondering, like, hey, 100 years ago, what was our conception of the universe? And what is our conception of the universe today and how is it different? And I wrote a small series of articles about like the biggest advance from each decade that happened in bringing us closer to our understanding of the universe. And I realized, this is the sort of story that I teach all of my students in all my intro to astronomy classes. And I try and give them this big sense of wonder, right? There are a lot of different ways to structure a class. And for me, I really loved that class, that intro to astronomy, that non-majors class, that class where, it's really only one of maybe two classes that people are going to take on science in college before they go out into the world and they never take a science class again. And I thought, the biggest thing I want to impart to people is it's not like, can you solve these equations and can you mathematically, determine the relationships between mass and radius and area and volume and orbital period and all of these other things that we care about in physics. And it was really more about, we have a whole cosmos out there. We have a whole universe out there beyond planet Earth. And yet we are here, one small species on one fragile planet in the universe. Can I give you an awareness of what science is and how the scientific process works? And can I give you an appreciation of how everything is better for everyone because of the scientific lessons we've learned from investigating the universe itself. And that's sort of how I structured my classes. And I realized there really isn't a book out there for people to read that goes along with that same spirit, that goes through what do we know and how do we know it, but that doesn't get bogged down in the equations, and that is full of illustrations to help you visualize these things that are happening on scales that are either much smaller, like subatomic, or much larger, like galactic and cosmological scales that we are just not familiar with. And that was really the motivation I had behind writing my book. And I've been very pleased to find out that lay people who pick it up because they want to know what's the universe and how did we figure it out are pleased with it, and that people who've said, hey, I want to use this for my introductory college class, that it's been useful for that too. And so I've been very pleased that this book has, when it's gotten into people's hands, that they've been really pleased with what it's been able to give them. The only two things I wish I could do now, because like you said, the book is from the middle of last decade. I wish I could have included gravitational waves, but we hadn't found any yet. And I wish I had included more about exoplanets, because that is an area of science that's really taken off, that was still in its infancy when I was writing that book.
Yeah. So you touched on something that I definitely want to ask about. I mean, absolutely. The 20th century, or the 100 years prior to 2015, right? That was a pretty good target date, right? Because it's like you're saying, well, if we look back 100 years from this year, Einstein was finalizing his theories on relativity, and everything that happened between that point and 2015, you had the realization that there are so many galaxies out there. Most of them are moving away from us. You had quantum mechanics, Big Bang theory, dark matter, dark energy. So, yeah, and several revolutions, as you just mentioned there, that have happened since. So right now, what are the big questions that are yet to be answered in the field of cosmology?
Well, you've already brought up some of them, right? We 100 years ago, a little over 100 years ago, we thought that the Milky Way galaxy was the full extent of the universe, that it contained everything. We thought the universe was static. We thought the universe was eternal. We thought that the universe was governed by Newtonian gravity, not Einsteinian relativity. We didn't really know very much about quantum mechanics. We had some hints from radioactive decays of elements. We had some hints from Planck's law and a problem that was called the ultraviolet catastrophe about why the sun didn't emit an infinite amount of energy at short wavelengths. But all of that has changed dramatically. We now know that our universe is not infinite and eternal in at least the part we can observe, that it had a birthday some 13.8 billion years ago, that it originated with a hot Big Bang, this hot, dense, rapidly expanding matter and radiation filled state. And today we even know that something occurred before that state to set it up. That's what we call cosmic inflation. We also know that the universe is not just filled with matter and radiation, but it also has some amount of antimatter in it, although it's less than the amount of matter in it. And we know that there is a new type of energy called dark matter and another type called dark energy that have to be present in order for for everything to add up. And so when we talk about what are the big unanswered questions, we want to know, what is dark matter and what are its properties? Where did dark energy come from and why do we have it at all? Why do the particles in the universe have the masses that they do and the physical laws? Why do they have the fundamental constants that they do and the structure that they do? Why aren't certain things present? Like, why aren't there leftover high energy relics that are everywhere from this earlier hot, dense state? How did the universe get the initial conditions it was born with? And those are questions that we believe the answer is in our theory of where the Big Bang came from, cosmic inflation. But that's another one that we aren't exactly certain. What was inflation like? What were its properties? How long did it go on for? Did inflation have a beginning? And if so, what occurred before that? We also don't know why our universe has so much more matter than antimatter in it. I think that there are a lot of smaller questions that are going to be answered, like, when did the first stars form? Can we discover how supermassive black holes formed and how they got to be so massive so fast? Can we tell whether dark energy is perfectly consistent with a cosmological constant, or whether there are some behaviors it exhibits that are more difficult to explain? These are the kinds of questions I see us answering in the next decade or two. But as for questions like, what is dark matter? What is dark energy? What is inflation and how did it get its start? And where did the matter-antimatter asymmetry in our universe come from? Those are bigger existential questions that I fear and I wonder what it will take to actually resolve those, because it's eminently possible that none of the observatories or experiments we have even designed today, they might not answer any of them. And so that's going to be a really interesting thing to try and uncover.
Well, yeah, and so in fact, the James Webb Space Telescope, I mean, this was designed from inception to address a lot of these questions. But yeah, it's certainly understood that, well, it can't be expected to resolve everything. Yes, we will most likely always have more questions than answers. And in fact, would it be fair to characterize it? It's like the 20th century, all these new areas of study. It's like we became aware of the mystery. We did not resolve them, not yet. Still haven't. But yeah, how is the James Webb just so well suited to help us in that regard?
Well, first off, I'd be a little more optimistic when looking back on the 20th century. We didn't just find like, oh, here are the questions we should be asking. Yeah, we did find those, but we found those by making discoveries. We found those because we looked at the universe in ways we had never looked at it before, and we were smart enough to listen to what it told us, right? The universe told us when we asked it, hey, what are you like? It said, this is what I'm like. And we said, really? Well, what does that mean? And then we ask again and say, okay, let me ask you in this more sensitive way. I see that you have this radio microwave glow everywhere in the sky. What is that like? And we found out that it has a black body spectrum and here's its temperature. And then we said, oh, okay, that's interesting. Well, how about imperfections? Are you a perfect black body or do you have imperfections? And so we went and said, well, we need to build a satellite to measure temperature differences. And that's where COBE and then WMAP and then Planck came from. And now we say, okay, we've seen all these imperfections. What do they mean? Where did they come from? What's their cause? And so it's sort of this balance between theory, experiment, and observation is that on the one hand, you say, okay, I have this framework and I'm going to construct my theory of, okay, here's the laws that govern the universe and here's the stuff that's in the universe. So what can I learn about where did it come from and what can I learn about how it grew up and what can I learn about where it's headed? And then you go out and you observe the universe and you say, oh, I expected it to be like this, but it's actually slightly different. It's mostly like this, but it's also a little bit like that. And so you start pulling all of these things together, and what brings you up to the present day is when you take that cumulative view, is you say, I don't want to look at one aspect that supports what I think or that favors my pet idea. You say, no, I'm going to look at the full suite of what's out there. And how far back can we see? And what wavelengths can we see it in? And what do we learn from that data? And then what you do is you ask, where am I missing data? Where can I fill in some of those gaps? And that's where something like James Webb really comes along powerfully, because Hubble can see back far into the early universe, but there's a limit because the universe is expanding. So light is redshifting, and there's a limit to how red Hubble can see. James Webb can see redder. It can see longer wavelengths. It's cooled to lower temperatures. So whereas Hubble would just see thermal noise emitted from the relatively warm spacecraft, James Webb can take data of what's out there in the universe at these sensitive wavelengths. James Webb has a bigger primary mirror, so it has more light gathering power, so it has better resolution. So that's what the big advantage James Webb is giving us. The JWST is seeing sharper images. It's seeing longer wavelengths of light, including broader wavelength ranges of light. It's seeing them with better instrumentation, with more filters, and it's able to better identify what's out there in the universe. If Hubble showed us this is what your universe looks like, then James Webb is in the process of just beginning to show us, how did the universe grow up? How did the universe go from that early uniform state with no stars or galaxies in it to the universe we have today? And what was it like at every step along the journey? That's what James Webb's big power is going to be as far as cosmology is concerned.
Mm-hmm. And the heat shield as well, right? This is also a key element there in letting the James Webb resolve temperatures from distant cosmic objects there, or rather back in time. That too plays a vital role in ensuring that it can see with greater sensitivity, yes?
Yeah, I mean, you have to have it at those low temperatures, because if it's not at those low temperatures, then you can't see farther out into the electromagnetic spectrum. Long wavelength light always means lower energy light. If with your visible light eyes, you can see, violet wavelengths down through red wavelengths, but you can't see infrared light. But if you had infrared eyes, you would be able to see, oh, guess what? The planet Jupiter shines of its own volition. And you'd be able to see, oh, there's a human over there across the way in the dark, but they radiate because they're warm-blooded mammals. Hubble can see that. Hubble can see that near infrared. But James Webb has to go much colder because it wants to see farther into the electromagnetic spectrum than Hubble can. So Hubble can take you out to about 2000 nanometers, but Hubble is in direct sunlight, even though it's coated in a reflective coating. Hubble is in low Earth orbit, and it's always, it's exposed to the sun quite a lot. James Webb has that unique 5-layer sun shield. James Webb is located 1.5 million kilometers from Earth, so it doesn't get the interference from Earth. James Webb also has on board a unique cryogenic cooler specifically designed for its mid-infrared image. The passive cooling of the sun shield takes it down to 40 Kelvin, which is great for observing up to about 5,000 nanometers. But in order to get out to about 28,000, 30,000 nanometers, which is the farthest wavelengths it can see, you have to get down to about 6 Kelvin, which is what the mid-infrared instrument gets cooled to with its onboard refrigerator system. So all of this, the reason you go to lower temperature is because you want to see that longer wavelength. And if you want to see the farthest objects of all, you need long wavelengths because the universe is expanding. Expanding space stretches the wavelength of light. So even if you emitted the same type of light that stars emit today, if you want to see it from back when the universe was 10% of its current size, or 5% of its current size, or 3% of its current size, then you need to have a telescope capable of seeing that wavelength after it's been stretched by the expansion of the universe. That's one of the uniquely powerful things about the James Webb Space Telescope.
And so to give a quick summary of that there, because this was said during the release of the first images. I cannot place the quote exactly there, but I'll certainly try to do a follow-up here. And it was not Bill Nelson who said this. It was one of the researchers who was attached to Hubble, and he explained how, so the COBE mission and, as you said, subsequent missions up to Planck, they mapped the cosmic microwave background from the late 80s to the early 90s, and with greater accuracy up till today. And then the Hubble Deep Fields campaign as of 1996 and onward. Yeah, these two things gave us the earliest images of the universe, but still only to a point. Much of the early universe was part of the shrouded in the cosmic dark ages, because we just didn't have the sensitivity to peer that into light that was that redshifted. And meanwhile, we had an image of the cosmic microwave background in the early universe, but there was that gap in between. And that's where the planning for James Webb, the inception, really began. It's like, we need to see all that in between stuff so we can match up observations with the earliest stars and galaxies to everything since about 1 billion years ago. And at that point, we can chart cosmological evolution over the whole time scale. And in so doing, right, we can figure out things like dark energy, dark matter, and the like. That's
the goal. That's the goal. That sounds like you're paraphrasing John Mather, because that's kind of how he talks. But when we look at the cosmic microwave background, that leftover glow from the Big Bang, we're getting one snapshot of the universe. We're getting a snapshot of the universe as it was about 380,000 years after the Big Bang. That comes because when you have this very hot, very dense state, You can't have things like neutral atoms because if it's too hot, all the electrons get stripped off of all of your atoms. So you just have this hot, dense ionized plasma. And what's interesting from a telescope's perspective about a hot, dense ionized plasma is it's opaque. You can't see through it. So there is this remarkable moment where the universe expands enough and has cooled enough that the wavelength of the light in it is now long enough that all of a sudden it doesn't ionize atoms anymore. When an electron happens to find an atomic nucleus and it comes down and binds to it, there isn't enough energy in your light for that light to reionize that electron. So when all of these atoms become neutral for the first time all at once, then all of this light that was previously bouncing around off of all of these charged particles, off of all the particles in the plasma, now that light isn't bouncing anymore. That light doesn't have things to collide off of. Instead, it just travels in a straight line. And we can see that today, even though it's more than 1,000 times longer in wavelength today than it was when those neutral atoms first formed. We can probe that. We can measure that. That's why it's called the cosmic microwave background, because these photons have been stretched to be in microwave frequencies by the time we're observing them. But you're right. Then you look back and say, okay, well, where are the earliest stars and galaxies that we've ever seen? And the answer is Hubble has seen them, but not for hundreds of millions of years. We know because the ones that Hubble see are already kind of mature and kind of grown up in their own way. It's sort of like looking back at a human being's album and you say, okay, I have a picture of you like 1 second after you were born. And then I don't have any pictures of you again until you're 5 years old. So I know that there has to be a toddler back before that. And I know there has to be an infant back before that. And I know there has to be like first words and first steps back before that. But when did they happen and how did they happen and where is that evidence? And that is what James Webb can look for. So I don't know that it'll be able to solve the mysteries of dark matter and dark energy. It really wasn't designed to do that, but it should be able to teach us aspects about the universe, like how do galaxies rotate when they're younger than they do today? It should be able to provide us pieces of information like what were the most pristine stars, the stars that formed from material that never formed stars before. What were they like and how were they different from the stars today? What were the very first galaxies of all like, and how were their properties different, and how early can we look back and still see supermassive black holes? Those are the kinds of questions that James Webb is really optimized to help answer, as well as all of the things that it can help answer about the solar system and stars and dust, because it's actually very well designed to answer many of those questions as well.
Yes, because, being able to see in a wide range of the infrared spectrum there, it's going to be able to see all this dust that's normally obscuring invisible light. And of course, James Webb is not primarily intended for investigating dark matter and energy. That's the stuff for follow-up missions, right? Like Euclid and who else?
Euclid, the Vera Rubin Observatory, and
yes.
the Nancy Grace Roman Observatory. Those should be exquisite at probing dark matter and dark energy. That's what those telescopes are designed to do, and those observatories are designed to do, both on the ground and also in space. Okay.
The naming controversy for the James Webb Space Telescope. Were you at all affected by that or wrapped up in that at all?
You know, there is normally a naming process for telescopes, right? Mm-hmm. Observatories, they have a whole naming process where the scientific community gets together and makes recommendations for what candidate names should be for the telescope or for the observatory. The James Webb Space Telescope is the only major mission in NASA history, as far as I know, in the history of all of NASA astrophysics. It's the only mission that did not have a proper naming process. It is the only mission that had its name chosen single-handedly by a now disgraced former NASA administrator, Sean O'Keefe. He unilaterally gave the telescope his name, and the community never had an opportunity to have their input listened to at all. This is not a telescope named for astronomers. And when you're putting out the message, as Michelle Thaler did on the press release, where the very first set of images were released, that this is your telescope, that this telescope is for you, that this is humanity's telescope. I think the idea that you could have one administrator name this observatory after another administrator it's really the height of absurdity. And so irrespective of whether James Webb, like what his role was in the Lavender Scare of the 50s and 60s, what his role was in making or in keeping NASA a place where gay people were not welcome. And regardless of how that legacy plays out today in 2022's America, all of which I think are legitimate issues, this telescope should never have been named the James Webb Space Telescope, because that is not how we name telescopes. This is not a name that is reflective of astronomy, astrophysics, or the community. This is a name that was given to us by outside forces, and now they tell us to live with it, regardless of who that name hurts. And that's I hope that that is the sort of thing that we look back on through the eyes of history and say, oh my, isn't this something that we should all be tremendously ashamed of, that we did this and we thought it was okay.
That is a good perspective to place into that sort of debate. So getting back to the subject of yourself and your outreach efforts, you have another book which is aimed at younger readers, called The Littlest Girl Goes Inside an Atom.
Yeah, that book should be coming out soon. I just finished writing it, and it's my first children's book, along with my co-author, Dr. Laura Manenti. And she's a particle physicist, I'm an astrophysicist. And, we were talking about how there are all of these children's books out there that purport to teach your children things like there's the baby Einstein stuff, and there's the quantum physics for babies stuff, and there's all of this, and it doesn't really teach you anything. It doesn't explain things to you, and it definitely doesn't explore that sense of curiosity and wonder with you, because we all imagine things like going inside an atom or flying through outer space when we're little kids. And then we have that beaten out of us. We lose that as we grow up. So this book is meant to sort of be a book that parents and older siblings and relatives can read with their young children, and can sort of explore these concepts of what lies down in the world of the microscopic, smaller than what you can see, and how do you see it, and how do you explore it, and what's down there. And I love the idea of doing it, but not stopping at like, okay, we got down to an atom and we're done. Like, no, teach them all of it. Teach them that atoms have electrons, and electrons orbit nuclei, and nuclei are made up of protons and neutrons are made up of quarks and gluons. There's no reason to not expose people to this right from the beginning. It's not too hard for them. What you do, in fact, by exposing them to like what's really there up at the frontiers of what we know, is you make it familiar to them. And so this is part of the thing. And, because it's a children's book, we had a lot of fun fitting it to a rhyme scheme and a meter, and making it, giving it that children's book poetry that I think is so much fun. And I'm really excited for that book to come out. we're still working on the final details, like the final illustrations with the illustrator. But I'm really excited for this when it's going to come out. I think it's going to be a lot of fun for everyone who gets their hands on a copy.
Mm-hmm. Well, I look forward to it. And speaking of which, you are also in the process of creating the Encyclopedia Cosmologica, which is going to involve some very beautiful illustrations and covers basically the entire history of the universe, one page at a time.
That's absolutely true. And this is actually what I'm in the process of writing right now. Is we had this idea to say, decades ago, they envisioned an Encyclopedia Galactica where we had sort of taken a census of the stars and star systems in our galaxy and what was out there and what planets were there and which ones were inhabited. And that's something we're still working on. But in the meantime, we've already uncovered almost everything that describes the history of our universe from the Big Bang 13.8 billion years ago until the present day. We know what the universe is made of. We know a whole lot of how it grew up. Why not tell that story to everyone in a format that's never been used before? So what we're doing with a couple of wonderful legendary space artists, John Lomberg and Mark Garlick, and with designer Will Lidwell, the four of us are putting together a book called the Encyclopedia Cosmologica, where we start before the Big Bang. And every time you turn the page, you get a full page spread of unique illustrations, unique astronomical art that was made by these artists that represent what was happening in the universe at this time. And I've written the text for it, and I've done the calculations to calculate how many stars and how many planets with life based on what we know about life and so on are there in the universe at this time, and how big was the universe, and all of these things that you'd want to know about it. And we tell the story of the universe one page turn and 100 million years at a time until you get all the way up to the present day.
Mm-hmm. Dr. Siegel, I feel like you're tacitly saying you performed the Drake equation.
The Drake equation was... I look at the Drake equation the way that, scientists today might look at, our ideas about quantum physics in 1910. Like, the Drake equation is wonderful and adorable before we knew that our universe began with a Big Bang, before we knew how old the universe is, before we had exoplanet data. There are still aspects of the Drake equation that one can still use, but also, there's a whole lot we know about astronomy and astrochemistry and astrobiology and biochemistry and origin of life studies and planets in the universe and how they form and where they form and when they form and what conditions they form under other. There's a lot more that we know now that we didn't know over 60 years ago when Frank Drake first proposed his equation. And although that equation still has its utility, it's also worth noting that there are some aspects of that still have substantial uncertainties, but also there are aspects of it that are now known. And we should not pretend that we are more ignorant than we actually are. Let's go ahead and tell you what we know, how we know it, and where there are still uncertainties, let's be honest about them. But let's not let those uncertainties stop us from telling the full story of what we know.
Now, is it accurate to say that you're hoping to have this book complete sometime in 2023?
The book should be completed sometime in the next 12 months and should be out before the end of next year for sure.
Okay. Are you still raising money through Patreon or?
I have a Patreon for what I do. I write the column Starts with a Bang, 5 new articles every week, plus podcasts, plus newsletters, plus ideally, if things go well, I'll be making science videos in the relatively near future. But in the meantime, yeah, you can support me on Starts With a Bang on Patreon. And if you're interested in pre-purchasing a copy of the Encyclopedia Cosmologica, I have a link that I can send over to you that you can drop in the show notes.
Absolutely. In fact, I was just going to mention all the ways in which people can connect with your work and hear from you. And yes, Starts With a Bang is available on multiple channels, which you can access from your website, startswithabang.com. And that includes podcasts and, yes, written work. And yes, and I also see that you wrote a book on Star Trek gear. And
yeah, I mean, that was so exciting. Star Trek: The Next Generation was my favorite sci-fi show when I was a kid, and I loved how it combined my love of space and the universe with this with idealism, with ethics, with the oh my, look at how good we can make life for people if we can just sort of, put our differences aside and work together for the collective good of humanity. It was like it combined my dreams of having science just explode in our society, and also having people use it for the collective good of all humankind. And it still is that. So on the 30th anniversary of Star Trek: The Next Generation, I took a look back at the technologies featured in TNG and in the original Star Trek, and to compare them with where are they today and how well have we done at making these technologies a reality, and which ones do we think are still impossible because of the laws of physics, and which ones are possible and it's just an engineering questions, and which ones have we already achieved or even surpassed what Star Trek's visions were of it. And so that book is called Treknology. And I'm happy to report that 5 years after it was finished being written, that is not out of date, that still holds up perfectly well.
Oh, well, great. Yes, I myself would be concerned about that, given just the exponential rate of technology and how quickly sometimes it's amazing how quickly we discredit science fiction written in the past, predicting the future. And yeah, the future has gone in a whole nother direction there. But it is good to know where we get things right, where we pull an Arthur C. Clarke.
Well, a lot of the times the science fiction tells us what we should be developing, even if it gets the how we're going to develop it wrong.
Oh, Ethan, I want to thank you for coming out, and I would definitely like to get you back on here to talk further about astrophysics and possibly to do a panel. Because if there's one thing I've found, talking to people from different fields and discussing the future of humanity, the future of space flight, there's a lot, there is one thing on the tip of everyone's tongue, and it is that we are in for some very exciting times. There's lots of challenges. We need to prepare for them in advance. And isn't it just so amazingly wonderful and sometimes scary to speculate about what will be possible and what we can do today that we couldn't before, and what we could be able to do down the road? That, I think, is something worthy of a panel discussion.
Yeah, well, if we can get the right lineup, I'll be happy to participate.
Yeah, well, still working that through, but I just thought of it the other day, so I'll let you know.
Thanks. Anyway, sounds good.
Thank you for joining us. I'm Matt Williams. This is Stories from Space.
We hope you enjoyed this episode of Stories from Space podcast with Matthew Williams. If you learned something new and this podcast made you think, then share itspmagazine.com with your friends, family, and colleagues. If you represent a company and wish to associate your brand with our conversations, sponsor one or more of our podcast channels. We hope you will come back for more stories and follow us on our journey. You can always find us at the intersection of technology, cybersecurity, and society.